All right, last example, number 5.
Let's get it.
So this one was taken directly off an AP exam. So again, this one, when we get down to like taking or finding the error on this problem, it's going to be something different, a little bit different than what we've been doing. Same idea, but there's going to be a little different. So I'll explain that when we get to that part. They are saying let f of x be sine of x squared plus cosine of x. The graph of y equals, this is f, it's not, of 5x, you have it on there, or the fifth derivative, shown at the right. So they give you the graph. Write the first 4 non-zero terms of the Taylor series for sine x about x equals 0. And write the first 4 non-zero terms of the Taylor series for sine of x squared about x equals 0. So again, this one says Taylor series. So sine x. What would be the first 4 terms of the Taylor series of sine x? Well, you tell me. It's a Taylor series.
Just for equals, so I'm going to say equals.
It's Taylor series, yes.
Wait.
It specifically says Taylor series here,
Okay, so.
not the Taylor polynomial.
Okay, so polynomial squiggles.
Yep.
Equals.
So they're asking here for the Taylor series. So series is equal to, so what is sine x? First 4 non-zero terms.
X minus x cubed over 3.2 plus x to the 5th x squared.
Okay, but I want it to be a series, so what do I have to do?
Dot, dot, dot.
Yep, and they don't ask for the general term, so if they don't ask for it, you don't have to put it.
Oh.
If you put the general term and it's wrong, you're going to get docked for it. So if they don't ask for it, don't put it, and then you don't lose points if it's wrong. Okay, so that is Taylor series of sine x. Now they said use that, because that's one we have memorized, to write the Taylor series for sine of x squared. Sine of x squared. So what is this one going to be? Three factorial, yep. Don't forget your dot, dot, dot. Again, they don't ask for the general term. So I recommend if they don't ask for it, don't put it, because then they can't mark you wrong if you happen to put the wrong one. All right, so that's all they ask for part A. Again, that's kind of a review back to previous sections too. Are we good with part A? All right, part B. Write the first 4 non-zero terms of the Taylor series for cosine x about x equals 0. Use this series in the series for sine x squared found in part A to write the first 4 non-zero terms of the Taylor series for f about x equals 0. Again, they're referring back up to this one. We're finding all these pieces so we can create this function. All right, so we need to find the Taylor series of cosine x. What is the Taylor series? Remember, you have sine x there, so remember what's similar and what's different about them. Odds and evens, where you start, pluses and minuses. So what is the cosine x?
1 plus x squared over 2.
I have, I think I have,
No, it's minus
yep,
x squared over 2.
minus,
Then plus x4 to the 4th factor.
and it's a series. Don't forget your dot, dot, dot. So again, if you look back up to the original f of x is sine of x squared plus cosine of x. So now we can try to combine those two. We have our sine of x squared and we have our cosine of x. So we're looking for sine of x squared plus cosine x. So let's write these in like an increasing order. So the first one, we have a 1 here. We don't have a 1 with sine x squared though, so we're going to start with the 1. Then we're going to add our x squared up here. We have a minus x squared over 2 factorial here, so we're not going to simplify until the end. Then I have a plus x to the 4th over 4 factorial. And I have a minus x to the 6th over 3 factorial. This one up here. Then I have the other minus x to the 6th over 6 factorial. Now, we need to see if we need to keep going or if we can stop here. They said they want the first 4 non-zero terms. But remember, we have x squareds that are going to combine, so that's only one term. So we have a term here. The x squareds become one term. X to the 4th is its own term. X to the 6th, they're going to become one term. So do we have the first 4 terms once we put them together? Yeah, so we're not going to have to worry about this x to the 10th up here, the x to the 14th. We're not going to have to include those because once we simplify, we will already have 4 terms here. Again, remember that's a series that they were asking for. So now we can work on simplifying the series. The 1's going to remain the same. X squared minus x squared over 2 factorial. What does that simplify to?
X squared.
Okay, so x squared over 2. Okay. And then we have the plus x to the 4th over 4 factorial. And then the x to the 6th over 3 factorial and the 1 over 6 factorial, we need a common denominator. So go ahead and figure out what the common denominator would be so we can combine those. We want one single term. Yeah.
Can you explain, like, I know you just said it, but like why we took all 4 terms from the cosine of x, but only 2 terms from the sine squared of x?
The reason we did that, it just so happened on this function up here, the sine x squared plus cosine x, this is the function we're trying to represent. So we know we needed to use sine of x squared and cosine of x. So I generated these two so I can use them to create this one I want down here. Okay? So I started taking terms from each of them. I took the 1 from here. There was no constant up here, so this is the only constant there. Then I know after I go constants, I'm going to go to the x's, but there's no x's. I go to the x squareds. Well, then I have x squareds in both. So again, those are going to consolidate to one term. X to the 4th is next because there's no thirds anywhere. So 4th power. Well, only one of them has to the 4th power. Well, this is my 3rd term then. So I already have 3 terms accounted for because we want 4 terms from this function.
Oh, okay. So
Then the x to the 6th is the one I go to next. Okay, they both happen to have that. When I combine them, that's going to be one term. So 1, 2, 3, 4 terms is what I'm going to end up with. And that's all they want. You could keep going on and using those, but they only want 4.
So you're just taking from like a constant. that
I'm
is
going up in
x
order.
squared.
Yep,
Okay.
going up in order. So the common denominator, again, you can multiply it out and get a value, but we want 6 factorial to be our common denominator. Did anybody find out what our value should be when we combine them? Yep, and we're going to have a minus there, minus 121x to the 6th over 6 factorial. So 121x to the 6th over 6 factorial. That's combining these two terms. Again, that's a series, so plus dot dot dot. If you can't read that or not sure what it says, let me know. Good with part B. Caitlin, we're okay with that?
Yeah, how did we find the common denominator of 3 factorial and 6 factorial?
So 6 factorial, I just calculated what that was. That was 720. That's what 6 factorial is. And then you can calculate what 3 factorial is and see, you can convert them to numbers and see, get your common denominator from there. Because then 3 factorial you have as 6. So right now 720 and 6 are your denominators. 720 and 6. So you need this one to be 720. So whatever you have to multiply by, that's how you get your top value, which happens to be 120. So negative 120 minus 1 more gives you the minus 121. All right, and I think that's all they're asking for part B. Are we good with that? All right, so now part C. They want you to find the value of f6 of 0. So what are they really asking there? What does that mean? When they're asking for this, what actually are they asking about? Think about the Taylor polynomials, all the sections we've covered. What are they actually asking for there? They want to know what this is. It equals what? Not exactly. They want to know the value of this 6th derivative at 0. So how can we tell that from all the work we've already done? Okay. So what do you mean by that? You're like right there. You're close. So remember, 0 is our center. And when you calculate a Taylor polynomial, you take all the derivatives, whatever up to wherever they want you to take. And when you take those derivatives, what do you plug in to generate the Taylor polynomial? What value do you plug in to those derivatives? That value at the center that they're talking about. So the center happens to be 0. So again, when you plug all those values into all those derivatives back in that first section when we learned that part, what were all those values? Where did we use those in the Taylor polynomial? Coefficients. So according to the work we've already done, do we have the value of the 6th derivative at 0? You said it was a coefficient. Coefficient of what? Negative 121, exactly. Remember, this is the 6th degree where that 6th derivative, all those coefficients, what we learned back from that first section, we took all those derivatives, plugged in those values, got all those coefficients. Remember, those coefficients were the value of the derivative at that point. So we already had it calculated. That was that coefficient right there, the negative 121. And that's all they're asking for. So if you want to write this so you have it for later, what this is asking for is the coefficient of the 6th degree term when the denominator is 6 factorial. It was the coefficient of the 6th degree when the 6th degree term when the denominator is 6 factorial. So that's that negative 121 right there that we found. Are we okay with part C? Yep. Alright, so part D gets us into what we've been doing this whole section. But again, this one is going to be a little bit different than what we've done. Same method, same formula, but you just need to have an open mind to how we're actually applying the theorem in this one. Okay. So again, we're not actually calculating the derivative in this one because they gave us the graph of it. So we're going to use the graph and analyze it and look at the intervals on the graph to help us find that upper bound limit. We know that it has to be less than that value on that derivative. Okay, so let's read it first. Let P of 4, so again, they're saying P for polynomial, but we wrote T earlier in the unit, so that's your Taylor polynomial at 4, or degree 4, about x equals 0. Using information from the graph, again, that's the one provided up above, the fifth derivative, show that the Taylor polynomial of 1/4 minus the function at 1/4 is less than 1 over 3,000. So again, this is your error that you want it to be less than. You want to show that with that fifth derivative up there, your error, the approximation, is less than 1 over 3,000. So again, they're just showing here, this is another way to say find or use the Lagrange error bound. This is the setup we had on that first page when we started talking about Lagrange error bound. We said this is the setup, you subtract them, take the absolute value. The error is the difference between the approximation and the actual. Okay. So what we're actually finding, this is the polynomial 4, so we're finding the remainder, or that error that we were talking about, 4th degree. And what value are we finding that at? We know the center's at 0, but where are we trying to approximate? Use the information they provided in letter D. Where are we trying to approximate? What value of x? Go ahead. Yeah, the 1/4. This is our approximation of 1/4 minus the actual 1/4. So we're trying to find the remainder, or the error, at 1/4. And again, we want that remainder, or error, that's what this is right here, we want that to be less than 1 over 3,000. Good so far? Okay, so again, that remainder, or error, we have that formula, the Lagrange bound, or the Taylor's formula for maximum error. So when we take the absolute value, and again, this is the 4th, so we're using the 5th derivative, and that's what they provided. So f5 of x over 5 factorial, 1/4 to the 5th power. Again, that's less than 1 over 3,000. Now this is where the problem starts to differ a little bit from the previous examples we've had. In the previous examples, they've given us either a function that we're very familiar with, and when we have a value that they've picked, we can look at the graph and visualize, okay, the maximum error, or the maximum value of the derivative on this interval is this value. Or they give you the maximum error and say the maximum error, we did that example, is less than 0.2. So they're giving you a value. In this one, they're not actually giving you a value, but they do give you a graph up here. So again, we know the center is at 0, and we're trying to approximate it 1/4. So pay attention that your interval here, this is 1 all the way over here, so this is actually 1/4. So they gave you a graph that's actually pretty nice to use because they broke it down into quarters already for you. So we know we're looking from here to here. This is the interval we're worried about. So this is the fifth derivative graph. And again, we want to know on this interval from 0 to 1/4, what is the greatest potential value of that derivative, so we can find that the error is less than that. So if we look at this, the value is actually right here. But by looking at the graph, can you actually determine accurately what that point is? No. Accurately, you cannot tell whether that's 35, 30, you're not sure exactly what value it is. So if you're not sure exactly what value that is, if you say pick 37 and you use that down here, you can't guarantee that that value is actually going to work out true, because you can't guarantee that that value is accurate. If they labeled that point, yes, you could use it. But what you need to do, again, we want to guarantee, kind of like that question Eric had the other day, it might have been yesterday, we talked about including the parentheses or brackets, but if you include them, that's just saying you're guaranteeing it's between those values. So what we're going to do here is you're going to go to the next upper bound that you can guarantee is true, that you know for sure, that you can guarantee it's less than. So what value do you think we're going to pick? 40. This is the next value that's slightly bigger. It's not much bigger. It's very close, but we can guarantee we know it's going to be less than that 40. Again, we're looking just on that interval, so we know that this point on this interval has to be less than 40, because this is the next upper bound that we can guarantee. Are we okay with that reasoning, that idea of that? Okay, so actually here then, the fifth derivative, the maximum it can be, we're going to use that 40, because we know it's guaranteed it has to be less than that on that interval. So we're going to have the absolute value 40 over 5 factorial over 4 to the 5th. And that has to be less than 3,000. So go ahead and calculate that. 40 over 5 factorial and 4 to the 5th. Did you find a value? What'd you get, Eric?
0.000032.
If you do math enter, will that change that to a fraction? I have a fractional answer. I want to see if we have this.
1 over 2017.
Yeah. 1 over 3,072. So again, what this question was asking, using that fourth degree Taylor polynomial and Lagrange error bound, they just wanted you to show that the error is truly less than 1 over 3,000. Did we show that the error was less than 1 over 3,000? Yeah. So this is what we found, and that's all they were asking. Is this true? And we showed that it was true, using the given information.
Instead of finding an interval like we did for other ones, we just proved.
Yep, all they're saying here is just show that this is true. And that's what we did. We showed that that was true. Okay? Again, they could go on from there and ask more questions about the interval, but they don't state specifically anything about an interval. They just want to know, is this statement true? And again, the key in that one, if they provide you information like this, it is acceptable as long as that value is close. Like, you don't want to use 80 or 120. That value is way too inflated. But this 40 we know is very close to this, and we can guarantee, without a doubt, because we know it's just slightly larger, that it will be included under that. Okay? Yeah, Eric.
So, I guess I'm confused. So, how do we know that we're supposed to find error there? I get that it has the absolute value and then the q sub 4, 1/4, f over 1/4. We didn't even use f for 1/4 because it really the problem that defines f is that sine cosine. We didn't touch that at all. So this is
Yeah, let me go back. Let me look.
I guess I'm confused what that's trying to say.
What this is trying to say here?
Yeah.
So if you go back to the first page, I know I have notes written all over this. Oh no, computer froze. There. Okay, this is the first page of the Lagrange error bound. So I know there's notes everywhere. This is what we've been using the whole time, right? This formula right here, finding that error. So we've been saying the error is equal to this. But what they're saying, just another way to state or ask the problem, they gave us this. Again, these all three things are equal. So they're saying this is the error. So they're saying, is this true? Is this less than this value? So instead of saying, is R4 of 1/4 less than 1 over 3,000? They said, is this less than 1 over 3,000? So these three statements are the same, so they just asked that question in a different way. Okay?
What does that all stand for? What is the t? Sub?
This is your Taylor polynomial, and that problem we just did would be the fourth degree.
Sorry.
Again, the a would be that 1/4 minus the function at 1/4. Okay? And then when we actually tried to figure out if it was true, we used this formula right here to confirm that, because these are one and the same. Okay? Does that help that out?
Yep.
Okay. All right, so we have finished 3.6, and you are done with Unit 3. So it's been a long time coming.